Welcome to the class. Today also I'd like to start the extensive coding class of industrial plant. Actually, the class title is problematic currently, but I will change this class name into industrial plant genomics programming something because I think that would be better for the people who try to register my class. Is that right? Okay, so let's start Jupyter Lab. Jupyter Lab allow root. I don't know if you actually following very well with my code because this is not that basic because I don't think that code itself is that difficult, but for you, especially who didn't experience any Python language before, so I recommend you to study more about Python grammars when so along with my code. So maybe you guys will have certain questions on the grammars, and I recommend you to study a bit about grammars, and also you can ask a question through the comment section. Okay. So last time, what we have done was that I don't know. Okay, what we have done. Something is not right. Network. Genome analysis. Network. Okay, so we made shared promoter pairs through our computer, but I say that it was really slow, so I changed the plan to run this code on my server. So my server successfully done with this code. So it produces shared promoter pairs all. Okay, so I will open this file. Okay, shared promoter pairs all. Also, I will give you this this shared folder in Google Drive, and I will post this website in the e-learning web page. Okay, then you can click and you can download this file. And also, I will upload this these files also. Okay, my Jupyter Notebook files. Then you can download these files and regenerate the result easily. Okay, so I will load this file and I will see the distribution. Okay, what is the distribution? This distribution is ratio common to the blocks. Actually, I almost forgot what was that. So I will check what was that. Okay, the ratio common to X block. So X block count, Y block count. So X block means the promoter blocks on X. So this was X, and second one was Y. And so these contain this number of promoter block, these contain this number of promoter block, and that was the common count is just 1. So between these two, maybe Tata box, right? And the ratio common, the common divide by X over this value. So I checked whether this value has certain distribution, and okay, there was distribution. So maybe we can, so if you have just like this value, then it is really where I say very common. I mean, from this distribution. But if you think you want to retrieve higher than 0.6, then these guys are not that common. So we selected the threshold 0.5 here and run. So I want to do this and do this. So I want this also more than 0.5 and this also more than 0.5. Okay, and I mask. So I call this data frame shared promoter pairs significant. So I put here sig. And also we downloaded the feature table that contains annotation of laboratory genes, and we indexed the laboratory genes, and we can check whether it has good format. Okay, so we have indexed using their product accession name. So this is the, I think this is GenBank ID, and this course assembly. But what most important thing is that the name, right? So we know the names. So what is the gene? We can easily observe. So I will remove this part, and we can apply the name annotation. Okay, so I used query ID, and this query ID goes into the data frame annotation, and it will call the name. Okay, so it will call the name, and the result goes to annotation X, and this is same. It will goes to annotation Y because it supplied query ID Y, and we calculated annotation similarity. So and we checked whether it has certain distribution on annotation similarity. So what is the idea? What was the idea? If you have, let me run this part. So we already selected a significantly similar, we retrieved the one pair of gene that has many common count, and which has this ratio, which is higher than 0.5, and the annotation, right? So this is the annotation. As we expected, similar functional gene would share the promoter region. That is something that we can say, okay, that is so obvious. But what if this annotation is not that similar each other? Then this common part will be very interesting. So that's why we try to calculate the similarity, annotation similarity. So we made annotation similarity and we limit the similarity less than 0.4. So 0.4 is located here. Not many things is reside there. And run. And the resulting thing is 46. And we can list up these 46 stops. Interestingly, many genes sharing their annotations, but the problem is this kind of result is not so good, I think. Okay. Uncharacterized ribosome ribokinase like, and this should be removed. This should be removed. Okay, so we don't want to use this uncharacterized. So I don't want to have uncharacterized, and I don't want this is included. And let me check what is the algorithm that we used. So similarity is calculated by this. So we just checked so we check the length of common and divide by just annotation x. Then I would say and length of, let me just copy it. I hate this complicated one, but that's okay. So I will calculate the length of annotation x and length of annotation y and use the minimum value of it. Run. So there's some things change it, and I will run this again. Let me check. So the value was 46, but now it's 30, and you can see not so similar each other. Not so. Dehydrogenase like and vesicle association protein and this and extension like, and I do not know why they are not removed. How are they calculated again? So this is just split by blank. Let me see the result of it. Everything should go here. Okay. Annotation y. So x will be, where is it? This is the location, the ID, index I mean. And x equal data frame location. No. What happened? Significant. Ah, sig. Okay, it returned 0.0. I do not know why. Let's check this one. And let's check this one. Okay. And oh my. Okay. Okay. So this is exactly similar, but it has this comma in there. So that's why then what I have to do is remove every comma there. Bit complicated, but it is not that complicated. So I put here, replace every comma into nothing. Nothing. Put here. None. And none. None. Okay. Now it becomes 24, not 30 anymore. Let me see. So the what was that? Pimbrim is gone. Pimbrims are gone. So I will say. These are network, I think. These are network. Now, so which means, so the reason why I'm thinking that is network, because this gene pair is regulated by same trans element. So these two must be, I should not say must, but I want to say must, okay? So theoretically, these two should be regulated by one trans element because it share the promoter blocks, okay? So I will come back with a module of network. So I don't have any plan. I didn't have any plan to build a network, but now I can see certain network here. So I will show you how to draw a network, because one person, maybe from other class, asked me how to use Cytoscape, but Cytoscape is not that convenient compared to the Python one. So I will come back soon with network X. Okay, hold on. Okay, I came back. Okay, so we have to install the network X, but how is very important. Network X conda. So there is network X in conda. So we should copy. And paste. Okay, everything is installed, and we can import. Let me save this first. This is the shared promoter pair sig CSV. No, it was filtered by annotation similarity. Okay, then let me close this one. Okay. Oh my god. Okay, no problem. Okay, and I will shut down this corner, and I will open new thing again. Rubber 3 promoter network 2 import pandas SPD, and also we want network X, S, and X. Okay, and let's open the share promoter pairs significant filtered PD share. Then we have this one, that is 24. Okay, good. And I will make graph. So let me make graph first, and X has graph class. Okay, so what is the G? G is network X class graph. So if you are said by Python, this is a class. What is a class? Class has many methods. So put dot here and put tab. Then there's many method that is previously defined by people who make this module network X. So maybe I will use node from and edge from. Okay, so node from, right? So this is the method, but you don't know how to use it, then just put this question mark on this method. Then it will gives you many instructions that will be very helpful for you. I don't know if this is okay. This is helpful. Okay, so I will use it. So let me add the nodes. So node means, what is the node? Network example image. Okay. So rain, grass. So rain and glass in season, allergy. this is node, but the direction, this line or this line is edges. Okay, so this is the terminology here. So we want add node first. So what is the node? Node is query x and query y. Every gene included here is node. So node is nodes are, not is. Nodes are. And this one, right? Okay. And this should be like this. Okay. Not like that. BIOS. Let me check the nodes. So in this way, but should be in one parenthesis. Label. Nodes. Okay, this is our nodes. So nodes. So we have nodes. Okay, we want edges. Okay. So edges. This is edge, actually. Okay. So this and this is linked. This and this is linked. This and this is linked. This is the edge. Okay. G add edges from edges. So this is already well done, and we want to draw. We want to draw it. Nothing happened. And this is because we didn't put matplotlib inline. Okay, this is the network, but I don't know why it do not draw any edges. Maybe it draw edges already, but not everything is linked to each other. So that's why it shows in this way. Okay, then I will check whether we can draw in different way. Hold on. No. Okay, we can calculate new position of each node using graph viz layout, but I'm not sure we have graph viz. Let me check. So we have to have this graph. Okay, we have graph viz. Okay, then we can pause graph viz and our graph. It calculates the graph and program netto. No module named pygraphies, so we need to install this pygraphies. Conda. Okay, let's install it. So this is also installed. The pygraphies is installed. And let me import this again. It's warning. Anyway, it is done, right? So it is done. So we can draw. Okay. So this is better. So this is better. There is so many program in graphics layout. So let me check if this also have information. So it has. I heard that there is many things like this. Let me put here. Okay. So this is the programs that they have. So if you change this into circle, then you okay. So this is interesting. But if everything is connected, then it will gives you the circular manner. Okay, or dot. Okay, dot is gives you back like this, and NOP. There's no NOP. Okay, let me erase. FTP, and on. Bit different. Okay. So this is how you can say, okay, we have network. 2 pi. Oh, this is better. Okay, and we can add labels. Okay. How do I add labels? Okay. No. Okay. Position and hold on. Let me check the draw. Check the draw. Okay, position. Okay, so we have to use this functionality. Then maybe we have to use this function and nx dot g also. So require position also. Okay, this is the labels. Let us improve. No, we have to add input matplot live pi plot splt, and let's configure. No, we add figure, and that figure size is 10 by 10. Very big, not very big. Let's increase twice size of this. So this is the thing. Okay. Hold on. I think we can change some label better than this. Hold on. Okay, so we can make a dictionary using this query ID as key and the annotation as value. Okay, so let's change. Let's make query ID first. Query ID and query ID y and values and label. So this is key. Keys. Okay. So BIOS will be like this. Okay. Annotation X. Annotation X. Annotation Y. Right. Okay. And we can zip the keys and BIOS and dict. Oh shoot, dict. Okay, this is the dictionary. Right? Dictionary key. So ID2 description. No. And so we can put here the dictionary. Then it will give you back the annotation rather than ID. But maybe netto is better to see the annotation, right? Then now we have certain landscape of the not interacting, simultaneously controlled by trans element. So let me check if this is right or not. What is most connected one? So this one is most connected one. Okay. So disease like resistance protein IPM1 like is associated with the sequoisolanol dehydrogenase and vascular associated one and vascular associated one. And let me check if this is really right or not. From previous research. Wait a minute. Okay, I checked everywhere to see any association is previously reported, but it was not that easy. So I don't want to do it here. Maybe I will do it later if I have enough time. But still, this is interesting that it has like a PARC9 and extension like is associated each other here. And here, PARC14 and extension like is associated through this one. So this is repetitively happen in this genome. So maybe there is, if we have enough interest in here, then we can, we can do more experiment to prove this is right or not. But we want to do some visualization of this result. So actually we made the visualization here. So get plot promoter using Querygene, right? And we can use it here also to see what is the visualization. What is the happening in the upstream sequence? But we need this data. So let's save this data to Picker. I already amount. So I need to load this again. Okay, this is the, split the set and I will on it. Okay, and let's make this one. Okay. and I will save this one to picker and promoter I and FO index. Pick. Then it is saved, and I will load this one to pick. Okay, 됐다. Right? So but the problem is we do not know the name exactly. So I need to check here. To retrieve this RPM one and I think there is a way to retrieve this network, sub-network. I forgot. Hold on. Let me use that one. There is very simple way to retrieve this community. Hold on. Okay, so we are extracting this one. So this one has number of neighbors, 3 number of neighbors. So we are calling it as a degree. So we can extract the degree for each node. So if you run this, then you can see there is so many information. So each node, whether each node possessing what kind of degree. So this neighbor, this node only one neighbor, so it has only one. But you know, so we have one node which contains 3 neighbors. So that should be 3 here. And as you can see, this is all dictionary format, so you can change this one into dictionary, and you can check more easy manner. And also you can change this into list items, and you can sort it items, and I will change it into list. Okay, then you can see more easily, and you can hold on. So if you put it in here, temporary. Okay, temp, and you can sort equal lambda x. Okay, and temp. Okay, and last one will be maximum one. And so max degree node. So this is the node, and this is the node name, and you can extract degree again like this, right? So you can see the number is 3, and what is the neighbors? So neighbors is at G. Okay. So they are neighbors. Okay. So edge data view. So everything is okay. And next, I won't change this into list. Let me check if this can be changed already. because I want to use the functionality. Okay, so you can make this into numpy array. I want to use the functionality of numpy. So numpy can be label, right? Okay. So let me set these four genes are subjected to max click. Okay. All right. So get plot promoter. Max click 0. What? Set is not sub. Okay. Let me change this into list again. Okay, let me make a title for it. Let's set title. 타이틀. 에 규진. Go. So this is another way to express title equal 규진, and I want to add annotation. We have dictionary. Okay, 규진. Right. So you have ID and annotation. This is better than the others. And maybe I want to add here AX. So this is another way to draw, to give them explicitly the place to draw. So I will change AX and set title. AX set label. AX ticks. Maybe this is not right. AX set Y label. Not to show. Okay, and plus subplots. We want to draw 4 subplots, pig and AX. Axis. And draw it here. This is 0. Don't. Okay, the first one is drawn, and that is okay. So AX. Okay, so and the pig size will be 10 to 5. No, 5 to 10. Good. And plot tight layout Very good. And so you can iterate. Click in max. Click. Click. Wait, and enumerate. And no, and good. Good. So you can see the situation with visualization, right? So the problem is upstream basis, but I bit set x ticks. I don't think this is right? So I think there is another way to express this one, but I forgot. So let me check for a while. Okay, so I found a way. So previously we made xticks using this command, but if you use ax object from axis, then you should use ax class specific command method. So first one is set xtick. So this method actually set up the range of ticks. So you can say, okay, I want. What is the meaning? So this means that I want to set the axis like this, but I want to label it. Use this one. Okay. So even though our data say, for example, 50, but we will map it in this way. Okay. This is what we have done last week. So run and run. Then we have this figure. But the problem is, actually, I hate it. I want to set the x limit. Set x lim. X lim should be 0 to 500. So everything is in same situation. You can see that even though the position is different each other, the situation is very similar each other. The location of blocks is conserved. This is really interesting. Let me change the color. See something. So we are doing iteration, and we are doing put color here. So color. This one should be color. See something. And this percent and get promoter. Yep. Pretty. 10 shows in this way. Not that pretty. Change this into 7. Oh, fair enough. So this is our first figure. Let me save. Figure. Shared block. What was it? RPM. This is centered by, I don't know. Then max degree. Shared block, max degree. PNG and DPI 100 beatbox inches height. Save figure. I think this one is our first figure. Let's save it. Maybe this is too big. Done. Ugly. 15 to 15. Okay. And preload. Save figure. And network of shared blocks. NG. DPI. I call 200 or 300? 300. 300 box, which is tight. 그쵸? Network shared blocks. I don't know why it's trimmed a bit in weird position. No. Yeah. This is not good. How do I avoid this weird trimming? Yeah. I think I need to ask. Okay, so I was trying to solve the problem that we are having. No. So we had some problem that some words is trimmed at the end of the graph, but I solved the problem in this way, and maybe you guys already have seen many times in the cytoscape. So how do you do it? So this is very simple. When you make a bias for the dictionary, then you will split it first. The description can be, so this is the description, and each blank can be split by this command, and you can join it with this enter symbol, okay? So enter symbol. So your bio become like this, and your final graph will be like this. Then nothing is trimmed in your graph. So this is cool, I think. And let me change this into 15 again. 15. And this graph is almost perfect, I think. Okay, this is really good. Nothing is trimmed. Very good. And you will see the high quality picture here, and you can copy, and maybe you can open up any word PPT. And I don't like this size of slide. I want to change it into A4. A4. Okay. So A4 will be better than A4. So let me paste it. Okay. So this is the network of ours, and insert certain information here. Figure 1, the network. This is a network, but what kind of network? Promoter sharing gene network. Promoter sharing gene network. So that will be controlled by shared trans element. Promoter sharing gene network. Putatively controlled by shared trans element. Is that right? Okay. So we have figure 1. Very good. And we have next one. We have another figure. Where is it? So this is another one. This is obey. Figure 2. I'm pretty sure at the end of this study we can publish this analysis, I think. Why is that? The promoter putative promoter blocks mapped to upstream sequences of predicted gene click. We need to explain what is click. Predicted click. Predicted click. Right. So we know that. So all these genes, the notation of all these genes differ each other, but it shares the situation. So this is a profile, right? So upstream profile is well conserved. Okay, so I like the words shared upstream profile. 좋다. Good. So So we have two figures. Let me save it. No. So I saved. And let me see another. Stops. This is not informative. Okay, let me draw it again. Another interesting stops. Hold on. So let me see this again. So we are just looking at this more than 0.5 ratio command to block, right? So I want bit is the threshold. Then maybe we can try more dense network. I have to learn everything. No. Stop it. Okay. We already have file. So we already have file here. And see the distribution. And let me ease the threshold. And none, and none, and none, and none. And the similarity. So it become more larger data set, and it will give us more dense one. Okay, I will change this also 6, and let me see. Uncharacterized. I don't like uncharacterized, so I want to remove everything uncharacterized. Okay, so I want this, what do we have saved? Almost I forgot again. What was input? Filtered by AS, but there is no filtered by AS, which means something is not saved before. Not good. Okay. So what is the filtered by AS? Like this. Then I will make that also like that. Okay. So this was the situation. And but I don't want to put it uncharacterized in both annotation. So how do I do it? First of all, I change this EDF temporary temp data frame. Temp data frame. Have no x, right? For x in. So I don't like uncharacterized. 그쵸? Uncharacterized in X. Mask 1. Mask 2. All these masks are all free here. We mask it. So this should be linked with or, because one uncharacterized is okay, but both, and one characterized is also okay. So this should be end, right? Okay, this should be end. Then, right? So temp data frame M will select everything that this type of condition is only supported by NumPy array. Port NumPy SMP. Cool. So everything that is uncharacterized should be here, and I will do it in this way. Then, okay, we have everything. So, to CSV 해서 보자. What was the shared something, right? AS version 1. Let me save it. Okay. Let's move to version 1. Key value, this dictionary, node and edge and graph. Okay. More dense graph will come out. I am hungry. It looks like this is too big. Again. Shape. Yes, that is too big. Yes, this is too big. Okay. Then, okay, let me edit bit here. So maybe you remember we have degree function, yeah? And I don't want to have any degree that is equal to 1, okay? And how do you x and y in degree and x if y is higher than 1. Okay, this is our selected node and G subgraph and selected nodes G sub and change all G into G sub and network blocks and sub. What? Key error. Why? Why? Why it doesn't have this key in the dictionary? Hold on. So I found the problem. So in the dictionary is not just by referred by this G-graph. So it actively search its its keys in this position. So as we made the subgraph, some of the keys in this dictionary doesn't have any information in this graph. So we have to make a sub dictionary of it. So let's change this dictionary using 4x in selected nodes, and let's have x, so key, no, value, right, and dictionary sub and dictionary sub x equal by u, right, and change this into like this, then all okay. So this is the graph. So we have now graph. So this is very interesting. So so this is really big network, and this is sub network, and this is this is largest, and this is next largest, and this another. So this is very interesting to see it, but I do not know why the singleton is existing here, because we already removed the nodes without any degree. Okay, so let's solve this problem next time. See you. Bye bye.